When developing pharmaceuticals, one major factor to consider is the efficiency of drug delivery into the patient's body. This is important so that the drug being administered can supply quick and steady relief to the patient and so that it may be targeted to the proper organ. Hydrogel beads may be used for researching drug delivery as they are biocompatible, and fixed law of diffusion may be easily applied for measurement of delivery efficiency.
The objective of this experiment was to investigate different factors that may affect the rate of drug delivery using calcium alginate hydrogel beads. The hydrogel beads were used to simulate a pharmaceutical capsule, while tartrazine dye incorporated throughout the beads simulated a drug. To simulate delivery into the patient's system, the hydrogel beads were added to a steadily mixed beaker of deionized water. As the tartrazine dye was diffused out from the beads and into the water, samples were extracted from the beaker in intervals ranging from 2 to 10 minutes, and the absorbance measured using a spectrophotometer to ultimately obtain the dye concentration of the surrounding solution.
The governing diffusion equation being considered in this experiment is as follows. Where F is the fraction of drug released, K is a constant incorporating characteristics of the macromolecular network system and the drug, T is time, and N is the diffusional exponent. F is determined by calculating mt divided by m infinity, where mt is the mass of drug that has been released at time t, and m infinity is the mass of drug released as t approaches infinity, or the steady state value. Taking the natural log of equation 1 yields equation 2, as shown. From this, we can see that n will be the slope and the natural log of k will be the y-intercept when the natural log of f is plotted against the natural log of t. To observe the effects of different conditions on these values, many different variables can be manipulated, such as temperature, mixing speed, dye concentration, bead size, alginate concentration, etc. We chose to look at 3 of these variables, namely mixing speed, bead size, and cross-linking time. The mixing speeds tested were 150, 220, and 300 RPM. The bead sizes were small, medium, and large, which were determined by the needle sizes available. The small beads were made with 0.7 mm diameter needles, the medium with 1.1 mm, and the large with 1.5 mm. Lastly, the cross-linking time was varied as 5 minutes, 10 minutes, and 15 minutes. Mixing speed, bead size, and cross-linking time were held constant at 200 RPM, medium-sized beads, and 5 minutes respectively, when they were not the variable being tested.
The solutions needed for this experiment include the following. A 10 gram per liter tartrazine dye stock solution, which will be used for the calibration curve. A 20 gram per liter sodium alginate solution containing 0.5 gram per liter tartrazine dye, and a 6% by weight calcium chloride solution with the same 0.5 gram per liter tartrazine dye. Notice the tartrazine concentration remained constant for the last 2 solutions. This was done purposely to prevent premature diffusion of the dye. Once the proper amounts of each solute were added to deionized water, each solution was left on a stir plate to mix until a homogeneous solution was created. For the sodium alginate solution, it was noted that homogeneity was not achieved for at least 24 hours, and that manual mixing was needed early on in the process. To calculate the concentration of tartrazine dye released into the water bath at a specific time in the experiment, a calibration curve was created using known dilutions of the tartrazine stock solution. Various dilutions were created until absorbance readings were measured on the spectrophotometer ranging from 0 to 1 to demonstrate a range of viable concentrations. Using these readings, a linear trendline was generated, enabling us to directly relate the measured absorbance of the beaker solution to the tartrazine concentration.
Sodium alginate consists of a polysaccharide bonded to monovalent sodium ions. When exposed to divalent calcium ions, cross-linking occurs as sodium is replaced by calcium. This linking of the alginate monomers results in a calcium alginate polymer. In our experiment, a syringe was used to drop sodium alginate solution into a calcium chloride solution, both of which contain an equal concentration of tartrazine dye. After the beads had cross-linked for the specified amount of time, they were promptly transferred to a filter paper and rinsed with deionized water. Once the beads had slightly dried, they are added to a beaker of deionized water and mixed at a constant rate by a magnetic stir bar. A stopwatch was started as roughly half of the beads were added to the beaker, and water samples were extracted from the beaker every 2 minutes. These samples were analyzed in the spectrophotometer before being added back into the beaker so that the volume would remain constant. After 10 minutes, samples were gathered every 5 minutes, and after 30 minutes, samples were gathered every 10 minutes until an hour was reached.
To obtain the data we're interested in, we need to start by converting all of the absorbances to concentrations using the regression equation from the calibration curve. These concentrations are then converted into masses by multiplying them by the known diffusion volume of 100 milliliters. These values represent the mass of tartrazine that has been released at each time interval. The final mass of each trial, or the one at t equals 60 minutes, is assumed to be the m infinity for that trial. Dividing mt by m infinity gives us a value for f. Now we have all of the necessary values to produce the 3 plots we're interested in. The first is a basic f versus t plot, which shows us how the fraction of drug release changes over time. Next is a df dt versus t plot, which shows us how the rate of change of the fraction of drug released changes over time. Last is the natural log of f versus the natural log of t plot. This one is the most important because it tells us the n and k values for that condition. The slope of the regression line is the n value, and the y-intercept is the natural log of k. These values can be checked with the exponent and coefficient of the trend line on the f versus t graph, because the equation of this line is in the form f equals kt to the power of n. The 3 plots shown here are for one of the conditions tested in our experiment. It is important to note that these plots only use the first 60% of the data in each trial because the empirical equation is only valid for that portion of the data. For an in-depth discussion of the results of our experiment, please see the article that accompanies this video.